Okay, this video is for AP Calculus. We're going to talk about one more application for the solution to differential equations. This one's called the Logistic Growth Model, and this is a favorite on the AP Calculus BC exam. So logistic equation model models population growth where there's an environment that doesn't allow population to grow forever, right? We've already seen unrestricted population growth. If we just say that the rate of change of a population is simply proportional to the population, that produces this solution, similar to the compound interest equation or radioactive decay. But that's pretty unrealistic because that means that, like, let's say you had rabbits. If you allowed them to breed and breed and breed and breed, you could end up with 500 billion rabbits. And obviously, that's not going to actually be sustainable in a real population. At some point, there is just not enough space. There is going to be a limit on the food and the water that's available, and you can't sustain that growth forever. Right? More realistically, an environment has factors which limit the population, like the availability of food, of water, or if you have predators in an environment, right? If there's just 10 rabbits in a forest, they can probably avoid the wolves, right? But on the other hand, if there's 10,000 rabbits in the forest, the wolves are going to get some of them, right? All right, so we're going to change this, and we have to have something that, as the population grows up, right? If we were to plot population versus time for unrestricted population growth, this is simply an exponential growth curve. It goes forever up like that. As some initial population goes forever. What we want is something that levels off. So at a certain point, it starts to level off and recognize that there is actually some maximum population that the environment can support. Okay, that maximum population we call the carrying capacity. It's the largest capacity that the system can carry, that environment can carry. And so the symbol for that is L. Right? Whatever this the maximum population that environment is can carry, we call that L, carrying capacity. And that means that as we approach L, the derivative has to shut off. We have to eventually have a slope which is getting closer to zero. So what we do is we take this population differential equation, and we just add a term here that says let's multiply by 1 minus p over L, because then as the population as the population is low, like let's say this starts out with 2 rabbits and we can have 1,000 rabbits in the forest, right? Then 2 over 1,000, this is very small, and so this is almost 1, so it's going to start with exponential growth. It's going to look just like an exponential growth curve. But at a certain point, instead of continuing to rise, when we're maybe at like half of the allowable population, 500, we want this to level off, right? And we want to start reducing this. So we start subtracting from 1, something that gets bigger and bigger as the population gets closer to L, right? And then when we actually get really close to L, like let's say we're at 999 rabbits, which is almost 1 shy of the actual amount we can have, 999 out of 1,000 is almost 1, which means 1 minus that is very close to 0. It's something like 0.001. Right? So by then, this population has effectively shot off to 0. The growth has shot off to 0. So by including this, we're allowing something to let the rate of change of the population just slowly decrease and keep it below this maximum carrying capacity. All right, so that means this is the differential equation that we use for what we call the logistic growth model. This is the logistic growth differential equation. Okay, and we're also going to memorize a solution, just like we memorized the solution to this equation is this. We're going to memorize the solution to this. But in this video, I'll show you the derivation of the solution. You're not required to do the derivation. We're going to do it once, and then we're going to memorize the result, because it's pretty involved. We can solve this with separation of variables. What we would have to do is multiply dt to the side, which means this whole thing here, p times 1 minus p over a, has to move to the left side by dividing. And then when we take an antiderivative, we're going to have to do partial fraction expansion over here because we have 2 fractions, 2 factors, and they're both linear factors. So what would that look like? Well, this 1 over p times 1 minus p over L could be a over p plus b over 1 minus p over L. And then we can say this A times this 1 minus P over L plus this B times this P has to equal the current numerator of 1. So effectively getting a common denominator, doing the partial fractions procedure. And then multiplying this out, we have A minus A over L times P plus BP equals 1, which means if we gather the P terms together, we have B minus A over L P's, and then we have a constant, which is A. And on this right-hand side, we have no P's, and we have a constant, which is 1. We can match up the P's to get B minus A over L is 0, and match up the constants to get A is 1. And then that means if A is 1, you can substitute in here and figure out that B is 1 over L, which means that this 1 over P, 1 minus P over L, is this A of 1 over P, and this 1 over L over 1 minus P over L. And then you can do a little bit of manipulation here. You can multiply the top and bottom of this by L to rewrite this term as 1 over L minus P, right? So this can be replaced with this. So in the integral over here, we can replace this integrand with 1 over P plus 1 over L minus P, split that into two integrals, and then do a u substitution on this one to get that this is u is negative dp. So then this ends up being 1 over P dp, the integral, and the integral of 1 over u du, and the integral of k dt over here. So this becomes the natural log of P. This is minus the natural log of u, which is L minus P, equals kt plus an integration constant we'll call C1. And then we're going to combine these two together because they both contain P. So using log properties, we can say that these two logs compress to a single log of P over L minus P, and that's equal to kt plus C1. To undo the natural log, we'll do e to both sides. So P over L minus P is equal to e to the kt plus C1, which is another constant I'm going to call C2, e to the kt, as that can be expanded into e times e to the C1, which is C2. Right? And then we're going to go ahead and multiply both sides by L minus P to get P equals C2 e to the kt times L minus P. Right? Then I will distribute this to both of these. So I have L times C2 e to the kt minus P times C2 e to the kt. And then I'm going to take this term and move it to that side because it also contains a P. So that's going to be P plus P C2 e to the kt equals L C2 e to the kt. And then we can factor out the P and divide this over to get what P is. This is the explicit solution. It's still general. It's going to be P is L C2 e to the k over kt over 1 plus C2 e to the kt. Okay, and then it's found usually with constants in multiple places. It's better to try to compress this a little bit. So there's some algebra manipulation we can do here. We can say, let's divide top and bottom by this C e to the kt. That makes this top become just L, this numerator, and this 1 becomes 1 over C2 e to the kt. And this divided by itself is a 1. And then I'm just going to swap positions here. This is L over 1 plus, and then I'm going to move this e to the kt to the top of this fraction to make it e to the negative kt. And then I'm finally going to relabel this constant 1 over C2 to be the final constant C. So this is the solution that we're going to memorize as a solution to the differential equation. Okay? So now that's a lot going on there, but let's just summarize this. Here is the logistic differential equation that's important to know. It is AP. It starts out as just like a regular growth equation, but it's multiplied by 1 minus P over L. The solution to that turns out to be P is equal to L over 1 plus C e to the negative kt. This L is the carrying capacity, the maximum possible population that's supported by the environment. And this K here is the same K as is in the differential equation. This C is not the initial population, so you actually have to solve it by plugging in a population time pair with the carrying capacity. All right. So let's do a couple problems. We're going to talk about wolf population in the forest. Okay. But first, we'll use the regular unrestricted growth population, and then we will use a logistic one. So problem 1 here. The wolf population, let's assume, has unrestricted growth in a forest. There's 20 wolves at time t equals 0, and there's 40 wolves at times t equals 10 months, what will the population be at 40 months? Okay, so the differential equation for unrestricted growth is this: dp dt equals kp, and we know the solution for that is p equals c unit kt. So I would make a table of information I have here, times and populations. Initial population is 20, the units here are wolves, and at let's see, 10 months, so now a time is 10 months, the population is 40. We want to know the time in the population, no, we want to know the population at 40 months. So this time we're being asked for the population at 40 months. All right, so we start with this equation. We'll plug in the 0 time initial condition first. So that means that population is 20 when time is 0. So that means 20 equals c times 1, and therefore the constant is 20. So we can write the model again with the 20 filled in, Okay, to establish the second constant k, we'll use the other known condition. We'll plug in 20 for the population, 40 for the population, and that occurs when time is 10. So that means 40 over 20 equals e to the 10k, which means that e to the 10k is equal to 2, which means that 10k is equal to the natural log of 2, which means the k is natural log of 2 over 10. Okay? And that turns out to be about 0.069315. So I'm going to go ahead and write that in. Now I have my model. P is 20e to the 0.069315 t. Now I should be able to plug in a population and find the time, or a time in a population. So to answer their question, they wanted the population at 40 months, so we can just plug 40 into the time, 20e to the 0.069315 times 40, and that turns out to be 92.674 wolves. And again, I would put the units on here, but I would not round this to the nearest wolf unless the problem said to the nearest wolf, what's the nearest wolves? Then, or the number of wolves, then I would round it to 93. But without that statement, leave it unrounded. All right, so that is the regular old from the last video lesson, regular old unrestricted growths. Right, at 40 months, assuming there's no restriction, the wolf population could get up to around 93 wolves. Right, let's do the problem over again. This time we're going to talk about the wolf population grows in a forest which can only support a maximum of 100 wolves. That's the carrying capacity, so that's L. There's 20 wolves initially, there's 40 wolves at 10 months. What will the wolf population be at 40 months? Okay, so in this case, we have this form of the differential equation with the term that shuts off the growth as p gets close to the carrying capacity. The solution is this standard form, and again, we're going to make the table of times and populations. When time is 0, there's 20 wolves, that's the unit, wolves. And then in months, right, when we're at 10 months, we have 40 wolves, and we're trying to find the number of wolves when the time is 40. So we'll use the 0 here. So the population is 20, so let's plug in. Population is 20, and carrying capacity, I can go ahead and fill in. That is going to be 100. Right, this number is 100 from the problem. Maximum number of wolves plus c e to the negative k times 0, right, which is 100 over 1 plus c, because e to the 0 is 1. So then we have to multiply both sides by 1 plus c. So I have 1 plus c times 20 equals 100, which means now I can divide both sides by 20, and that's 5. So that means that 1 plus c has to equal 5. So c has to equal 4, just verifying. Right, so now that I have that, I can fill in that constant, and my new updated version has 100 for the carrying capacity, and it has 4 in here. So notice that c is not the initial population. You have to plug in p and 0 or P and the time to find C. E to the negative KT. Now we have one more constant to solve. We'll use this initial condition to do that. So I'm going to plug in 40 for the population. 1 plus 4e to the negative k, and that happens when t is 10 months. So we can do the same thing, multiply this and divide by 40. We're going to get 1 plus 4e to the negative 10k equals, I'm swapping positions, 100 over 40, which is 10 fourths, which is 5 halves. Okay, then I'm going to subtract 1, so I have 4e to the negative 10k equals 5 halves minus 1, which is 5 halves, minus 2 halves, which is 3 halves. And then I'm going to divide by 4, so e to the negative 10k equals 3 halves divided by 4, which would make that 3/8. All right, so now, taking the natural log, negative 10k is equal to the natural log of 3/8, and then when I divide by negative 10, I get that the k constant is, it turns out to be about, so this natural log of a fraction is negative, so these negatives cancel, and we get positive 0.09808. 0.09808. Okay, so now I can write this one more time and fill everything in. I'll do that over here. P equals the carrying capacity of 100 over 1 plus C is 4. E to the, now I have to have a minus in here because of the formula. And then let's see, 0.9808. 0.9808 times T. Right, so now I can plug in, use this model to answer their question. Population at time 40 is 100 over 1 plus 4e to the minus 0.09808 times 40, which turns out to be 320.004 volts. Is that right? That can't be right because that is larger than the other one. And that wouldn't be possible because that would be over the maximum number of volts. So my answer key is wrong. Let's do this over again. Let's see, 4e to the negative 0.09808 times 40. Add 1. 100 divided by that number. Correct answer is 92. I'm getting 92.667 volts this time, which makes me wonder if this number was correct. Let me go back and check this number that we did before. We had 20 times e to the 0.06969315 times 40. Yeah, that's what's wrong. This previous example was 320.004 volts. And my answer keys are swapped for some reason. All right. So yeah, when we had unrestricted growth, this population versus time was starting out with 20 volts and growing exponentially. And by the time we got to 40, this was all the way up to 320 volts about. But in the logistic model, population versus time, the system can't go above 100 volts. So this 20 has a curve that looks more like this. And by the time we get out to 40, it's clamped off, right? The food supply or whatever has prevented the wolves from growing as fast, and so we're only up to about 93 volts because we've already started to shut off the derivative here of growth. All right, so that is, make a note that those are reversed. That's a classic example of the two. All right, just to bring the point home, here is the unrestricted growth. Here's the carrying capacity limiting this, so the curve is going up and down. All right, so that's the logistic growth model and how it works if you're just working with the equation. Now, there's a couple other things to know. With unrestricted growth, right, the rate of change always is constantly increasing. The slope is continually increasing. But that's not true here. right? This curve is concave up for a while, right? So it starts out at concave up, but then at a certain point, the curve starts to be concave down, right? And where does that happen? Where does this switch from concave up and the rate increasing like exponential growth? When does it start actually having a concave down behavior where it's still the first derivative is positive, it's still increasing, but it's increasing less and less. It turns out that whatever the carrying capacity is, this inflection point happens at half of the carrying capacity. So that's an important fact to know. Sometimes questions will ask, what is the time when the rate of change is largest? So the slope of the tangent line here is increasing right up to this point. That is the point where we are at max rate of change. And beyond that point, once we go at a time past the point where we're at half the carrying capacity, the rate of change starts decreasing. So that's an important fact to know about logistic models. Right? So we can figure out where that occurs. The max rate of change occurs wherever that second derivative is zero, right? This is a proof that that's true. I think this video is pretty long already, so I'm just going to pause. You can pause the video if you'd like to read this. This is the proof that shows that the max rate of change occurs when the population is at half the carrying capacity. But we're going to keep talking about more facts about this. So typically, we would start with an initial population which is under the carrying capacity, like 25 volts or 30 volts or something. Maybe you have 100 as the carrying capacity here. And that means that the curve will be generally concave up until you get to that place where we're half the carrying capacity. Then it switches to concave down. And we never will actually reach this. So I haven't really drawn this properly. This blue curve would not actually ever reach the carrying capacity. Right? What would happen if you happen to have too many wolves? Like you just plopped 160 wolves in this forest where only 100 can survive. Well, then the population will decrease. We'll have a decreasing function that's concave up, also approaching that same level. So you can think of the carrying capacity here as the stable state. That's where the population is stable. If you're below that, it will tend to rise to that. If you start out above that, it will tend to fall. And we do know that at half the carrying capacity, that's where this changeover happens, where we are at max rate of increase and then the rate starts to decrease. Okay, so the things you need to memorize. Memorize the form of the differential equation. That's important for some questions. Memorize the form of the standard solution. Memorize that L is the carrying capacity, which is the maximum population, and memorize that the max rate of change and the inflection point occurs at when the population is at half the carrying capacity. Okay, how many more problems do I have? 2 more. Okay, so let's go ahead and take a look at a couple of additional problems. These are all similar to the way things would be asked on the AP test. We're getting further through the course now, so we should be talking more about AP wording. A population Y changes at a rate modeled by this differential equation, where T is measured in years. What are all values of Y for which the population is increasing at a decreasing rate? All right, increasing at a decreasing rate. Well, first of all, I would probably look at this and say, hey, I think this actually is logistic growth. It doesn't state that in the problem, but we can put this in our form. So this is why it's important to know the differential equation form. Right? Logistic growth has this form. The rate of change of the population is Kp, starts out as exponential growth, but then it has a 1 minus P over L term here, right? So could we, in fact, can we put this into this form? Well, I think we can, because if we're starting out with, we've got dy dt is equal to 0.2y, and then 1,000 minus y, then I notice that, well, my standard form has a 1 here, but I have 1,000 here. So what if I did this? What if I just divided this by 1,000? So everything in here I'm going to divide by 1,000. And then I'm going to multiply by 1,000 out here to compensate. So that means I could rewrite this equation as dy dt is 20% of 1,000, which is 200y. And then this would be 1 minus y over 1,000. And now I can see that my carrying capacity is 1,000. So whatever this population is, the maximum amount of it in the environment is 1,000. Okay, so it says, what are all the values of y for which the population is increasing at a decreasing rate? Now that I've verified that this is a logistic model, I have a picture in my mind of what the population curve looks like, right? The maximum is the carrying capacity 1,000. This might start out at some value, like if I were to plug in, well, I don't know what this is, there's no time for me to plug in here, but presumably there's some initial population here, but this will grow to a certain point. And then when we get to 1/2 of L, which is 500, then this will start to shut off and eventually stay underneath the carrying capacity, right? So what is this asking? This is asking for the y values where the population is increasing, so that means the first derivative, so the first derivative y prime is positive, but it's increasing at a decreasing rate. So this rate is decreasing, which means the second derivative would have to be negative. So I need something where the curve is increasing, but the concavity is down, which means the curve shape has to look like this. Well, where is that true? That's true here, right? The population is increasing, but it's increasing at a decreasing rate. And that means these are the y values. So for what values of y is the population increasing? I would say, if this was an AP test, I would say the values of y for which the population is increasing at a decreasing rate are, and then I would show an inequality, y between 500 and 1,000. I'm not going to put the equals case. It can't get to 1,000, and right at 500, we're not yet decreasing. So I would say between 500 and 1,000. Okay, so that's an example of how they might need you to know these memorized facts in order to do equation on the AP exam. All right, let's look at one last question. This has a bunch of parts to it, but they're all related. All right, so at time t equals 0, a bacterial culture weighs 1 gram. 2 hours later, the culture weighs 4 grams. The maximum weight of the culture is 20 grams. Write a logistic differential equation model that models the weight. Okay, well, let's do that. That means dp dt, I'm going to use p for the population of bacteria, is equal to kp times 1 minus p over L. That's the population. And let's see. I think I can go ahead and fill in a couple things here. I can go ahead and say that this is kp1 minus p over 20, because I know that that's true. I'll save this constant later. I'm going to fill it in a later part, because when we solve the differential equation, we'll end up being able to solve for this k. Right, so let's actually work on part B, which is where we're going to solve the differential equation. So for part B, I know the general form of this solution we've memorized as P is the carrying capacity over 1 plus C e to the minus KT. And that's the general form. And now I'm going to make a little table, times and populations. At time t equals 0, this weighs 1 gram. 2 hours later, so that time is in hours, the culture weighs 4 grams. So by using this, I can figure out, use my color scheme here. The population is 1 when, let's see, the carrying capacity is 20, so I can fill that in. 1 plus C, we don't know, e to the negative 10 times 0. So that's 20 over 1 plus C, because e to the 0 is 1. That's kind of hard to read. Let me back up there, because that's going too hard to read. 1 plus C e to the negative 10 times 0, which is 20 over 1 plus C. And that means that 1 plus C, if I multiply that to the other side, has to be 20, so C has to be 19. So now I've got another version of my model. I can fill in 20 for the L, and I can fill in 19 for the C, and then we have minus KT. So to find the K, I'll use the other initial condition. When the population is 8, the time is, when the population is 4, the time is 8. Okay, times 8. So multiplying that out, we're going to have, I'm going to multiply this to this side and divide the 4. So that's going to be 1 plus 19e to the minus 8k equals 20 over 4, which is 5. So 19e to the minus 8k is 5 minus 1 is 4. And yes, and then e to the negative 8k equals 4 over 19. So negative 8k is the natural log of 4 over 19. So k is the natural log of 4 over 19 divided by negative 8, which turns out to be 0.77907. 907. Right, so now I can write this model one more time, and that is that P, I'll just continue down here, P is equal to 20 over 1 plus 19 e to the minus 0.77908 t. Now we have a complete model, and that's the answer to part B, is the solution to the differential equation with all the constants filled in. Okay, now that I know my k is 0.77908, I can go back to part A and finish part A, because I needed that k and it's the same k. So that means the differential equation is dp dt is 0.77908p times 1 minus p over 20. This is the differential equation that matches the solution. Okay, then it says to find the culture's weight at 5 hours. So for that, we're simply plugging 5 into this. And if you do that, you just plug 5 in there, you get 14.426 grams. If I did this correctly, my key, hopefully I did. And then when will the culture's weight reach 18 grams? For that one, we're going to have to solve a different color here. So for D, when will the culture's weight reach 18 grams? We put 18 in for population weight and solve for the time. 1 plus 19 e to the minus 0.77908 t. And then let's see, if we multiply both sides by this, divide by that, you get 1 plus 19 e to the minus 0.77908 t equals 20 over 18, which is 10 over 9. If you subtract a 1 from that, you get 10 ninths minus 9 ninths would be 1 ninth. Then you can divide by 19 and get that e to the negative 0.77907, actually 907, looking at my key again, is 1 ninth divided by 19, so the 19 joins that on the bottom. You can take the natural log and you don't have to do this. T ends up being 6.600 hours. So that's the time when the population. So once you have a full model, you can plug in the time and find the weight, or you can plug in the weight and find the time. Okay, the only last interesting one here, a little different. After how many hours is the culture's weight increasing most rapidly? Okay, so for that, you have to know that this increases most rapidly when the population is half of the carrying capacity, which is, let's see, 10 grams, half of 20. And so then you would have to say 20 equals 20 over 1, 10. Half the carrying capacity is 10 grams. So 10 for the population equals 20 over 1 plus 19 e to the minus 0.7790. I think it's 7 actually, t. And when you solve that, you get the time when that occurs is 3.778 hours. Right. So that's the last example. There's a lot going on there. Just go back to what you didn't memorize. In order to do these kind of problems on our tests and the AP exam, you want to memorize all this. Memorize the form of the differential equation, the form of the logistic model, the fact that L is the maximum population carrying capacity, and that the max rate inflection point happens when the population is at half of that. All right, and that's it for this video series on differential equations for AP Calculus.